Formal Lab 1, Falling Fruit. So our project takes inspiration from Newton and the apple. So we know the story of Isaac Newton as he watched an apple fall from a tree. But we're interested about other fruits and what other variables might play a role in things falling. So our question is, will fruits of larger masses have greater momentum and total energy as predicted by energy and momentum conservation in inelastic collision? So our research design, we have four fruits. We have an apple, an orange, blueberry, and a peach slice, and we're using a meter stick and we're dropping from consistent heights and 12 points minimum and frame count equals 1. And to minimize inconsistency, we're recording data inside so there's no wind problem. And then we're dropping from a height of 1 meter for each fruit. And then models reflect fruit masses and set axis with origin at end of meter stick. And some inconsistencies we found is that drop pathways were not equally linear and acceleration didn't align with gravity.
And then we provided system schemas and energy diagrams, and it's important to note that these models are reflective of the equation of the conservation of momentum and mechanical energy. And it is also important to note that momentum is conserved for an inelastic collision, but kinetic energy is not. So first we see for the blueberry that the distribution of energy at point 1 is E total is equal to energy potential. And with that equation described as mass times Earth's gravity times height, at point 2, the total energy is mainly potential, with kinetic energy increasing as the fall proceeds, presented by point 3. And finally, at point 4, the blueberry comes into contact with the ground, and the total energy of the system is transferred as heat to the ground as internal energy. The same distribution of energy is the same over all four fruits, as the falls in systems are consistent. However, the total energy will not remain the same, causing the pie charts to increase in size for fruits of larger mass. And we see that here with the orange, which is the highest mass, having the largest pie charts, and the apple, which is the second largest, having slightly smaller pie charts, representative of the total energy in their systems.
So in descending order, we started with the orange trial, which weighed at 186.9 grams. In the top right corner, you can kind of see the setup of our experiment. We dropped every single fruit from 1 meter, and we set the origin of our charts to where the meter stick meets the ground. And then just notice the main trends of the position velocity graphs are negative, and the acceleration graph has a positive correlation. And this is the data from the orange that we calculated on Excel. Along with the apple that weighed in at 136.5 grams, we see the same relationships. We have a negative correlation for position and velocity, but a positive correlation for acceleration. Then this is the apple data as calculated on Excel.
Peach weighed in at 1.6 grams, and for the peach trial, again, we see that there is a negative trend in the position and a negative trend in the velocity, and also the acceleration, which differs from the other trials. And here is our peach data from Excel. And then here we see the blueberry, which weighed in at 0.6 grams with a negative trend in position and velocity, as well as a positive trend for acceleration. Here is our blueberry data from Excel. Our main findings, we're looking at the velocities. We can see that there was not really a trend of larger or smaller velocities based on mass, and they fall over the same range from the line of best fit from position from tracker. They are also pretty comparable to the average velocity calculated on Excel. The accelerations were notably not negative 9.81 meters per second squared, which was expected of gravity, and there is something we are unsure as to why. However, we saw that the apple had the closest acceleration to gravity on tracker. However, the average velocity found on Excel was smaller for most trials. Additionally, we can also see for both tracker and Excel that the standard deviation is largest for the acceleration values of the blueberry, apple, and orange. We also compared the total energy for each system that we predicted with solving for the potential energy at point 1, as the drop just starts and the total energy is made up of potential energy. As expected, the total energy is greatest for the largest mass orange and decreases based on mass. And finally, the coefficient of restitution is close to 0 as expected of an inelastic collision for all trials except for the blueberry, which we did not expect, but this is the only trial that bounced.
So then for our physics, we expected velocity to increase as the fruit fell due to the acceleration of gravity. And we expected this acceleration to be the same for every fruit, regardless of mass, which would be negative 9.8 meters per second due to gravity. And then you can see the kinetic energy and potential energy conservation equations below. And then in the middle of the slide, you can see how mass would actually end up canceling out. So the velocities are expected to be the same for every fruit. And then the differences in between the fruits in overall energy is that as the mass increases, the overall energy of the system would also increase. Unfortunately, our experiment did not confirm these observations. Our acceleration due to gravity was not negative 9.8. And this could be due because of air resistance or variation in where we place the tracker points. There's also a lot more uncertainty when we calculated it on Excel versus using the tracker data. And this is also kind of the same trend with velocity as well. Air resistance could have affected this and variation in tracker points, and the collisions may not have been completely inelastic with the ground. So improvements that we could do would be doing multiple trials per fruit and averaging these out, or consider different drop heights